Hello, most wonderful geometry class. I'm going to begin with the Chapter 5 review, and I have a couple show and tell items I shall reveal throughout the video, which I'm sure you will thoroughly enjoy. So stay tuned. All right, first one. When we notice that this and this are intersecting right here at the midpoints, then we know that this is a mid segment. Two things from Theorem 5.1 tell us that, number one, this and this are parallel. Okay, so you would be able to tell all sorts of things, like you'd be able to say, okay, then those angles are the same because they're corresponding angles. Or you can say those angles are the same because those are corresponding. I'm going to sneeze. Oh. But what we're going to head toward is not the fact that these are parallel and can produce equal angles, but that this segment length is 1/2 of this segment length. Or you could think of it as, which I like to do rather than dealing with halves, I always just multiply the smaller one by 2. So we have 3x minus 9 equals 2. And may I say 2 of the x plus 5, not 2x plus 5. You have to have the x plus 5 in parentheses so that you can distribute. So we have 3x minus 9 equals 2x plus 10. And I'm going to add 9 to both sides, and we get x equals 19. Now let's double check to make sure what did they ask in the question, because maybe they asked what the lengths of these sides were, but indeed they did not. They asked for x. I need to, whatever. I was going to shut off my email, but last time I shut off my email is when this whole thing disconnected and I had to start over. So if you hear dinging, sorry. All right, number 2. A little hard to read, but it does say the perimeter of ABC is 96. And we have to somehow find x. Well, because you are given same, we have all sorts of mid segments going through here. So we have lots of connections. So we have, this is the mid segment of this side. So if that's 2x, what is this whole side? That's right, it's 4x. 2 times that. And if that's 3x plus 2, I'll get a different color. Then that's the mid segment to that side, BC. So what's twice 3x plus 2? Remember, you got to multiply both by 2. So that's 6x plus 4. And lastly, we have, okay, I'm going to not be clicking these the whole time this time. We have that and that. So again, that is the mid segment to that. So if this is 4x plus 1, this whole side is twice that. So 8x plus 2. So we'll go back and add up my perimeter, which is 4x plus 6x plus 4 plus, wow, what the heck is that? It's supposed to be 8x plus 2, but it looks like I forgot the x in there. All right, and what does that equal? 96. Draw your line. Let's combine like terms. So this is the same side of the equal sign. So on this side, we're just combining. We're not adding, subtracting, and all that. 4x plus 6x is 10x, plus 8x is 18x. 4 plus 2 is 6, equals 96. It's only now that I'm going to start subtracting and adding. I first had to simplify the side. Subtract 6, divide by 18, and 90 divided by 18 is 5. All right, when we get to these, and again, both of those at the top, we use the mid-segment theorem. Okay, the mid-segment theorem, which was theorem 5.1, theorem 5.1. So you should have, I asked you, I believe, if I'm remembering to do it, to look up each of those theorems for each problem, so you know what am I actually using here, so we're not just guessing. All right, so now we have the situation. Let's analyze what we have. It looks like we have two angles that are the same. Looks like we have right angles, and we're given these. Okay, so that would make this a what to this angle? That would make that an angle bisector. And if you look up, hopefully you found out that it's theorem 5.4 on page 295, the angle bisector theorem, or something like that. It said that if you have a side, an array that bisects these two angles, then there's somewhere on this bisector where you can draw a line such that it's perpendicular. And when you find that spot where it's perpendicular, those two sides are the same. Okay? So I can't just start drawing randomly everywhere. I have to, and there's more than one. I mean, you could do this and this. The key is that they have to be perpendicular. So that means those are the same. So we're going to do 7x plus 3 equals 10x minus 9. We are going to draw the line. We're not going to get that 4 mixed up in here. Subtract 7x first. Left with 3 equals 3x minus 9. Add 9. 12 equals 3x. Divide by 3. Divide by 3. X equals 4. Oh, I said I wasn't going to do that. All right, orange. So when we get over to this one is actually using, hopefully you found it, theorem 5.2. The perpendicular bisector, theorem 1, page 293. And that one says that if you have a perpendicular bisector, which this is the perpendicular bisector, not this. Okay, it's the line such that it cuts it at a 90 and cuts that segment into two equal parts. So the only thing here that's cutting another segment into two equal parts is this line right here. Okay, when that happens, you can pick anywhere on here and the distance to those vertices are the same. And such that, here we go. This is the same. So I have 4x plus 6 equals 6x minus 3. I'm going to move the smallest x term first. Move the numbers together. Divide by 2. 4.5. Okay, number 5 is, it's black. I do not want black, and that's black. How many blacks do I have? Oh goody, that's blue. This one, this is in theorem 5.7 on page 303, talking about the in-center. What were the in-centers? That's when you have angle when you take all of the angle bisectors and where they meet. So see how this one is the bisector? I can tell because these are the same. And this is the angle bisector because these two are the same. So where those two meet right here, when I can do a perpendicular to the sides, and those are all going to be the same distance. This one, and actually this one too. I don't need that third one, but it is true that all of those are equal, and that is by that. That's called the incenter when you have the angle bisectors and you find the concurrent point, the point of concurrency. So we're going to set those equal. So I had this one was 2x minus 3 equals that one, which is x. Okay, don't get confused by something like this. It's the same solving procedures. We need to get our x's together. Okay, there's a 1 before this, so if I subtract 1x from both sides, I'm left with x minus 3, and then what's left over here? 0. Just put 0 though, don't leave it blank, it's 0. Add 3, and x is 3. Number 6 deals with the circumcenter. Good, I have another blue one. Wow, 3 different blues. This is cool. Okay, so the circumcenter, oh, it looks the same. Oh, darn. Is it the same? Oh, a little different. Circumcenter, which deals with perpendicular bisectors, the point of concurrency of perpendicular bisectors. And that's theorem 5-6 on page 301. So it's saying find the perpendicular bisector. So here's one. It's perpendicular and it bisects that side. Here's another. It's perpendicular and it bisects that side. And here's another. It's perpendicular and it bisects that side. When you find that point of concurrency, it is an equal distance to the vertices. So this is equal to this, and actually it's also equal to this straight across. Again, that's the circumcenter, and so we can say those are equal. So what are those? 3x, it looks like, equals 5x minus 8. Draw the line. I'm going to want the x's here, so instead of moving the smallest one, I'm just going to move the x's over here, so I have the x's on one side. But don't lose the negative. Okay, be very careful. You get x equals 4. Okay, so hope you got those. You know, sit with things and literally go through it and point things out to yourself. What do I have here? Okay, I got 2 angles the same. Oh, okay, that means I have an angle bisector. You know, what do I have here? I've got 2. These are the same. I have perpendicular. Oh, perpendicular bisector. So try to walk through some of this and analyze what you have. All right, number 7. We're using theorem 5-1, page 285 on this problem. It says, suppose EP is equal to PG. EP is equal to PG. Explain how you can find measure of angle PQG. This one. Ah. Well, folks, what do you notice? Those are the same. Those are the same. So therefore, these are midpoints. So this is a what? Mid segment. So therefore, these two lines are parallel. And if I knew the distance, this would be like, let's say this is 4, then this one is 8. But I don't have distances, and I'm looking for angle measures, so that probably isn't going to be helpful in this case. But what I do know is that I need this angle, and I have this. And if you're familiar with parallel lines, you know that those two angles are corresponding. And as long as the lines are parallel, those are equal. So it will be 85. Measure of angle PQG equals 85 degrees by the, well, explain how you can find it. Okay, so I would say PQ is parallel to EF by triangle mid-segment theorem. And then we can say angle PQG is congruent to angle EFQ. This isn't a formal proof, so we can skip the switching it from congruent to equal measure kind of a thing, by corresponding angles theorem. If EF and PQ both have a slope of 2, what can you conclude? If these both have a slope of 2, you can conclude that those two exact lines are parallel. Okay? Because since they have the same slope. And if they're parallel, that would mean that this is a mid-segment of that triangle. So you can kind of work backwards. Although, oh yeah, you would know that because you have these two, the sides are equal. So honestly, I'm looking for that part of it more than anything. Recognizing that two lines that have the same slope, parallel. Okay. Time for a commercial break. Today we have LaCroix, Karate. We have Cerise Limon. We've got a cherry lime, naturally essenced sparkling water for my beverage. Looks like it's 0 calorie, 0 sweetener, 0 sodium equals, I guess, innocent. Okay. All right, we'll go with that. Of course, I always recycle. We can't see. Is this blurry or what? There, please recycle. Alrighty, I will do so. Gotta thank Mrs. Peters for that. Had one of those at the Well-Read Mom Book Club and thoroughly enjoyed it. Hence purchasing it at the store today. All right, onward we go. I hope all of you took a breather. Nice good drink of water. Water is good for the brain because now you need to draw all sorts of things on this triangle, or you should have. So we got to first draw perpendicular bisector of AC in pencil. So I put these different things in here. Pencil. So be careful. Perpendicular bisector of AC. So perpendicular, it's going to go straight up and down. Bisector means it has to go halfway in between. So the perpendicular bisector would go right there. Angle bisector of A in red. Okay, let me get my red. Where's my red? Oh, that is disgusting. Who took my red pen? Hang on. Huh. Guess I'll have to use the non-erasable one. Angle A. So we need to bisect angle A. So I need to go exactly halfway. So those are the same. I need a median in green. Okay, a median. Anywhere. What does a median do again? Goes from a vertex. Green, I just feel like doing that. From a vertex, any vertex, to the midpoint across from it. So it would go right there. And draw the altitude of AB in blue. So go AB. So the altitude is going to go straight such that it's perpendicular. So I'm not trying to hit a midpoint here. I'm just trying to make sure that when I leave this vertex, it hits it perpendicularly. If I went from here, I could have went straight down here. That's also an altitude. Could have went straight down over here. Wow, that's angled. That's just a bad drawing. There, that's better. Okay, so there's many options. Those aren't the only ones, except for it does say altitude of AB. So wrong on that. Good thing I used Erasable for that one. I did it. I didn't have that option. It specifically said of AB. The only one that was anywhere was the median, the green one. Okay. Now we move on into centroid. Remember, centroid is the point of concurrency of the what? Medians. Okay, and we did the median up here. Remember, the median was in green. It went from a vertex to the midpoint. Okay, so when we come down here, it says O is the centroid. So I know that these are all medians now. And that's important because I know medians cross and divide it up into thirds. Okay, so let me see here. What would be the best way to do this? I'm trying to think. This is like, you know, worth 2. So it's kind of like 1, 2, and 3. I think what I'm going to do is do this equals 2 of these. So that I can, instead of trying to split this in half, because it's, remember, this is one part and then there's 2 parts over here. So it's either I have to split this in half or I have to double this. So I'm going to double that because that's easier. All right, subtract. Four and a half, does it ask us for a side? No, it asks us for x. Okay, next one, same thing. Now this is the one part. And this is the 2 parts. So again, I just think it's easier to double in a case where it does. If this was like 4x or something, I could divide it by 2. Nice, that'd be great, but I can't. So I'm just going to double this one. Just don't forget to double both parts. So I have 4x minus 14 equals, or plus, no equals, sorry, 3x. Okay, subtract. Remember, there's a 1 here. Okay, so just remember 1 part, 2 parts. So sometimes that's easier in your head to see. And it works, usually it's easiest if you double the 1-parter. Sometimes you can split this in half, depends. All right, so we go down to centroid, and those are the intersection of what? Medians. Again, we're just gonna make sure we got these medians down, aren't we? All right, so here we go. Here's another fine picture, and it says find MK and DK. So where's MK? First, let's get that MK, and then the whole DK, the whole length of that. And I know this is 8. So again, this is 2 parts. This is 1 part. So if this was 2 parts, and that's 8, 1 part would be if you divide it by 2. So MK equals 4. And then the whole thing from D to K would then be the 8 plus the 4, which is 12. All right, LM is here. We're going to find that, and we got to find LE, again, the whole thing. And here we go. They gave you the 2-parter, which is 6. So the 1-parter is half of that, which is 3. So LM equals 3. And LE equals 3 plus 6, which is 9. Write an expression for FJ. Okay, where's FJ? FJ is this whole thing. So honestly, you could do it like 3 different ways. You could say 2x plus 2y. I mean, you can't figure it out. You could say, let's see here. Let's say we were gonna, this is the 1-parter and it's 2y. So how many y's would that be over here then? If I just turn this into y instead of the 2x. Be 2 of these, right? 2y and 2y would be 4y, plus these 2y would be 6y. Or we could do it all in x. If this is 2x, that's the 2-parter. What's this? Half of that, 1x. So 2x plus 1x is 3x. So any one of those would be fine. I'll accept any of them. Contradictions. See which 2 statements contradict each other. Triangle ABC is a right triangle. AC is twice the length of BC. Okay, could be, I don't know. A, B, and C are all equal. Okie dokie artichoke. How's that going to happen? How are you going to have a right angle and have them all be equal? That means these would all be 90, and 3 times 90 is 270, and a triangle is 180. So again, those, something should go awry in the head. That does not go together. Let's take a look at the next one. Triangle XYZ is acute. Okay, so that means, well, first of all, let's look at what we have. We have this. Okay. I don't know why they actually gave you that, but okay. So it's acute, so that means all the angles are less than 90. This is saying isosceles, so you could do that. You could do that. You could have those two. Now this is saying that x is greater than y, which is greater than z. Okay, so that is implying that we have 3 angles that are all different. Which one of those would that contradict with? Isosceles, where there's 2 angles that are the same. This, by this being bigger than this, which is bigger than this, it tells you all 3 are different. Okay. .42 pens laying here. Okay. Explain how you find the orthocenter of the circle. So these are just ones I want to make sure that you study these and know the difference between each of these. So we've got all 4 of them here. We've got the orthocenter, circumcenter, centroid, and center. So I'm hoping that you have looked these up. These are all explain how you'd find it. They all start out the same. Find the point of concurrency of what? And then find the point of concurrency of what? Find the point of concurrency of what? Find the point of concurrency of what? Okay, so what was the orthocenter? Those were the altitudes. Circumcenter was the perpendicular bisectors. Centroid was the median. And incenter was the angle bisectors. So I guess just make sure you kind of study those and know that those go together. Okay? Use indirect reasoning to show that an equilateral triangle cannot have an obtuse angle. So remember, what's our very first thing we want to do? We want to assume. Assume what? Assume the opposite of what you want to prove. So it says we want to prove that an equilateral triangle cannot have an obtuse angle. So we are going to assume that what? Exactly, that an equilateral triangle can have an obtuse angle. Okay. So then now we go into that description. This is the part that it can look different for everyone. Explain to me. Okay, explain to me. Use logic in an orderly way. That's all I would say. So I would say, okay, assume that the equilateral triangle can have an obtuse angle. Okay, well then I would say, well, since equilateral triangles have 3 congruent angles, then all angles would be obtuse. So the measure of all 3 angles would be greater than 180. And a triangle angle measures, angle measures equal 180. Therefore, you have a contradiction. And the assumption that you made up above is false. So, an equilateral triangle cannot have an obtuse angle. So again, this part can be, different wording. Just explain to me how having an obtuse angle, you can even write numbers. You could say triangle ABC and start giving me measures and say, no, because if this was more than this, then all 3 of these, A, B, and C, would add up to be this. And it can sound a little bit different as long as you get to the same point. All right, look at the bottom. List the angles from smallest to largest. All right, so let's see here. Well, I just think anytime you're going to do something like this, you should just draw yourself a little picture. So just go ahead and draw ABC and do it. AB is 3, BC is 4, and CA is 5. Okay. Smallest goes across from the smallest side. So the smallest one is angle C. And the next smallest would go about the next smallest side, which is 4, and that's angle A. And across from the 5 is angle B. Okay, draw myself another one, or I could use the same one and erase it. So AB is 20, and BC is 12, and CA is 10. All right, so the smallest one is across from the 10, so that's angle B. And the next smallest across from the 12, so that's angle A. And then the biggest one is across from the C, or across from the 20. So I'm hoping those are really simple and straightforward. Those should be the nice ones to have. And now we're getting into, here's the angles, you tell me the sides. So it's just the same thing, but the opposite. So again, just to make sure you don't make mistakes, draw yourself a little triangle and put them in there. 30, 60, and 90. Well, that is definitely not a 90. But anyway, I'll get the point across that we know the shortest is across from the smallest. So across from the A is the side BC. And since we are listing sides, we do have a segment bar above them. All right, across from the 60 is the next smallest, which is AC. And across from the 90 is my biggest side, which is AB. Again, draw a triangle. I'm going a little fast because I'm hoping these are pretty straightforward. Oh wow, this is again another really bad drawing because now this is clearly not 100, but it doesn't really matter because we're just trying to get the labeling correct, which Hopefully you're seeing the connection here, because when you're going across from the B, it's the other two letters that you have. So, and across from the C is BA. Again, these could be flipped, AB, BA. And across from the 100 is BC. All right, so that's that. Now let's get on to this complicated picture here. It says complete these with less than or greater than in here. So first thing I need to look at is BC and ED. But I want to first see what I have. Okay, so I've got these angles are the same. I got these sides are the same. These sides are the same. These sides are the same. This is a right angle. Okay. All right. We can do this. So what is the side BC? We're looking to say some kind of relationship between that one and that one. Well, let's just start getting some sides. Actually, I think it would be easier, because right now I'm like, what? So let's start figuring out numbers, because I see this 7, this 7. These are the same, so that's going to be 7. And that's going to be 7, and that's going to be 7, isn't it? Now, what about angle measures? Let's go over here. If this is a 90, and this is an isosceles triangle, what are each of these? 45 and 45, for sure, we know that. Oh, and look at here. We know this is 88, and this is an isosceles triangle right here. So what's 180 minus 88? Okay, so 92, and then we want to split that in half. So divide that by 2. 46. Okay, so we're going to put the 46 here and the 46 here. All right, we're cruising. We are cruising. Oh, yeah, and look at this. 777, equilateral triangle. So even though they only show these two angles are the same, it's equilateral. So this has to be the same as well. So these are all 60. Nice. Nice, nice, nice. Okay, well, we can figure this out then, can't we? Because we have two congruent triangles here, people. This is called side angle side inequality, the hinge theorem. We have this side and this side with this angle in between. And we have this. I'm not even sure we need to do all that other stuff, but that's okay. This side and this side with this angle in between. So since we have side angle side and side angle side, the angles across them we can compare. Or the sides, I'm sorry. So BC is across from the 88 and ED is across from the 90. So which one's bigger? Ding, ding, ding. All right. And BEC is what to BEA? Well, we figured that out. That's bigger. And then let's look at these sides, BC and BA. BC and BA. Again, it's that side angle side inequality. Wait, which ones? Wait. Oh no, we can do this. Yep, side angle side, side angle side, side angle side, so we can compare the sides across from them. So BA and BC, this is across from a 60, this is across from an 88. So this is bigger. I think there's probably a few other ways you could have looked at that, to be honest, but that's how my brain saw it today. Let's see it different tomorrow. I do know you have to use the side angle side inequality theorem though there to just make sure that those triangles can be, that you can compare that side across from it. You have to have the two sides being the same in both of the triangles before you can compare the side across from it. All right, we are almost done. the base of the isosceles triangle. Okay, again, picture person here. Gotta do this base. So these are the same. The base of a triangle has a length of 25. Okay, so I know these are the same by the isosceles triangle theorem. What can you say about the lengths of the side? What do you think? These got to be the same. And we've got this. It's 25. So if you spread this side way out, could each of these be 12.5? No, because these have to be the same, right? So they have to be the same. So we got 2x, and it's got to be less than that third side. You have learned that. Any two sides of a triangle have to be less than the third. So when you divide them, x has to be less than 12.5. All right. Very good. Very good. Wait, oh yeah, that's right. There was a couple more things I was going to do. Could you do this right now? So, pause the video. I gave you triangle ABC, vertices. I want you to find the points of concurrency for the circumcenter of ABC and the orthocenter of ABC. Okay, and then tell me that coordinate. Okay, I'm going to work through it, but I need you to pause the video and then come back to it, okay? All right, so I'm going to first graph I'm going to put the ABC on both of these so I can do them separately. So, oh, these lines look so small. Negative 3, 1. 1, 2. There's A. Negative 3, 4. B. 1, 1. Okay. Try to draw them really straight or use a straight edge. Because if you're drawing the other lines, that's going to be helpful. And negative 3, 1. Negative 3, that's A. 1, 2, 3, 4, it's B. All right, so there are those. And somebody keeps beeping. Now we got to do the points of concurrency. So what was the circumcenter? Who can remember what the circumcenter was? We went back to here. The circumcenter was the perpendicular bisectors. Okay, so if you look on this and do just the perpendicular bisectors, watch how cool this is. So I'm going to take the straight sides because I can easily see that. If I do the perpendicular bisector, well, first of all, it's got to bisect it. So it's going to go through here, and perpendicular means straight up and down. So it's going to go straight up and down. Again, some of you will want to use straight edges. Drawing straight lines doesn't come easy. And then we are going to find the perpendicular bisector of this side. Well, this one is 1, 2, 3 apart. So you're going to be in the middle here. And then it's going to go straight across, right through the middle. And look where that lands. Voila. What point is that? That is negative 1, 1, 2.5. All right, hopefully you did the orthocenter, and hopefully you did that one right. The orthocenter, let's go back again, and that's why I want you to make sure you study these, altitudes. So we need the altitudes of each. So what was altitudes again? It was the sides that were perpendicular. Okay, altitudes were perpendicular to the side, okay, from a vertice. So if I do the altitude, let's pick this point. It looks kind of confusing, but if I do the altitude from here to this side, it's right there actually. It's the side. If I do the altitude, I pick a point so I don't get confused. Altitude from here to the side across from it. Oh, look at it. Again, it's right there. And if I pick an altitude from here, this one will also go through there. So all three altitudes cross right here at -1, 2, 3, 1. Okay, remember it's take one vertex perpendicular to the other side, another vertex perpendicular to the other side, another vertex perpendicular to the other side. So sometimes you have to extend the lines past it or out here, or it's on the line, so it just depends. So when you do an orthocenter of a right triangle, look where it lands. Pretty interesting. So, oh wait, I didn't do my show and tell, and we're already done. It's my book. Yes, that's right. I want to show you my book that I talked about in class. Ooh, look at that. This is that wonderful 2-pound book. Gold, the little thing. It's like opening a... Whoa, did you hear that? Yeah. Isn't that beautiful? Oh, doesn't it just want to make you read it? So when you're done studying for your math, you can get a good book and cuddle up and read. Nothing better. Well, math is definitely more fun, but reading is a close second. So take care. Cheers.